Welcome back, and to wrap up the videos in this section, we are going to just talk about the error bounds and the sum bound for the comparison test, just as we did with the integral test. Okay, now again, this is an optional video, so you don't have to review everything here, but let's just kind of review what we know about the sum and error stuff based on the comparison test. So if we know that our sequence contains all positive terms, and if a series converges, we know that we have to have the condition given to us that Bn converges, then that implies that An is convergent by the comparison test. Again, we would need to prove Bn is convergent, but if we look at the remainders of each term, if we say Rn is the remainder of the A sequence, or the A series after we sum the first n terms, T is the remainder after, or for the last n minus or n plus 1 terms for the B series, then according to the comparison test, right, we know that the series An is less than the series Bn, so that means Rn must be less than or equal to Tn. So that's kind of useful, and maybe it can be more useful if we're able to find a nice series to compare to. Okay. So if we can also use geometric or p-series. That's those nice series that I was referring to. So if we look at this and say the sum of the first 10 terms, okay, so this might be our series. I don't know what it is exactly yet, but the sum of the first 10 terms, we can calculate that to be 0.283596 or so. Now if we look at this sequence as a whole, so we're going to call this sequence An. We're thinking An is going to be convergent, so then we're saying that this is going to be less than or equal to, if we get rid of the 1 in the denominator, that makes the whole denominator smaller, which results in us dividing by a larger number, so the whole value gets larger, that is. So it becomes we're going to say that this is less than or equal to n over n times 3 to the n, which is the same as 1 over 3 to the n. And that's convergent by geometric series. Converges by geometric series. Okay, so then if we look at this, right, this we can find its entire infinite sum, and we would just have to take the first term, so that's 1/3 times 1 over 1 minus 1/3. And once you calculate all that out, we end up getting a half. So we know the entire infinite series for 1 over 3 to the n converges to 1/2. So then, okay, so now what? I'm still thinking that, okay, this from above, right, we have Rn is less than Tn, and I know, okay, so this whole thing, this is like T, and so I want to say, okay, I know R10 plus S10 is equal to 1/2, and maybe let's use T10, just so we're consistent with notation here. So T is corresponding to the B series. Okay, so then if I want to look at the remainder, so if I'm trying to approximate the first 10, or the error here, we can say, okay, the R10, so that corresponds to the A series, is going to be less than or equal to T10, right? But T10, well, and okay, I'm trying to keep my notation consistent here, T10, and this is going to be equal to 1/2 minus T10. I should, okay, let's use the remainder. Okay, I need to maybe develop some new notation. The remainder for the B series corresponding to the first 10 terms. Okay, and now that the B series is a geometric series, so I can find the sum of the first n minus 1 terms. So from n is equal to 1 to 10 of 1/3 times 1/3 to the n minus 1. And we might have to dig out an old formula book for the sum of the first n terms of a geometric series. It ends up being 1/3 times 1 minus 1/3 to the 10th power over 1 minus 1/3. And crank on this long enough, and what I got was 8.467 times 10 to the minus 6. Okay, so a little tedious, but ultimately what we're doing is using this idea that if we can find the error bound for this nicer series, right, this nicer BN series that we compare to, we can find a bound for the sequence that the series that we're actually working with. So what I did is I found my B series that I wanted to compare to, which is a nice geometric series. I found its entire infinite sum of 1/2, and then said, okay, partial sum plus the remainder is equal to 1/2, and then use that as a bound for the series that I'm actually working with.